All right.
Yeah, welcome everybody to the Schubert seminar of the day. So we have Marco Castronovo speaking, but let me just announce first next week, and that's a week from now, December 2, we will have short talks by graduate students, and we have two confirmed so far, Kevin Summers and Franquis Caraballo Alba. But today we are excited to have Marco Castronovo from Colombia uh, speaking about cluster gluings and open string Schubert calculus. Please go ahead.
Okay, thank you for the invitation. So the work I'm going to describe today is joined with Misha Gorsky, Jose Simental, and David Speyer. Um, so let me start with some motivation from the theory of schemes. So let's say we have a collection of schemes. I'm going to denote each of them by X or X, so the scheme and the structure sheet. And it's a family, so they come with an index I, and the indexing set could be infinite. Okay, so they're schemes. And here in my picture, I have two of them, Xi and Xj. Then one of the things we learn in the theory of schemes is that we can glue them together. If I have, let's say, a map phi ij from an open subscheme uij inside xi, we target uji with image uji, an open subscheme in xj, and this map is an isomorphism between these two open subschemes. Then I can use a family of such maps to glue the schemes together, as long as this family satisfy a certain compatibility condition. So, for example, we could ask that the open set for indices II is the entire set, with the gluing map being the identity in this case, and whenever we have three indices ij and k, we can look at intersections uij, uik inside. So imagine a third, second open set here, uik, for example, and look at how these gluing maps behave on the overlaps. So if they behave like this, meaning they make this triangle commute, some sort of co-cycle condition, then they give you a consistent way to glue. So the gluing scheme as a topological space will be just the topological space that you obtain by gluing things together. But the structure sheets also glue together, so you get a scheme. And a basic question one might ask after seeing this construction is, if, let's say, we start with affine schemes as pieces, is the gluing scheme affine as well? And there are pretty straightforward examples that show you that the answer is no. But so the example, I'll give you one such example for those of you who have never seen any example. But I'm not going to give the simplest example. I'm going to give an example that will be instrumental for what I want to say later. So the example is as follows. I'm going to denote GR24, the Grassmannian of two planes in C4. And we can think of this space as the space of full rank 2x4 matrices. So I'm denoting such a matrix, like a generic such matrix like this, modulo row operations. And we can compute some numbers out of these matrices. I'm denoting xij, the determinant of the ith and the jth column of the matrix M. For indices I and j that run between 1 and 4. Let's say 1 is less than j. So these are the famous Fukaya coordinates, and they give you projective embedding of this space into P5. And it turns out that in this case, the image is cut out by a single equation. So it's a hypersurface. And the equation is x13, x24 is equal to x12, x34 plus x14, x23. So it's a quadric. Now, so the scheme that will be an example of gluing in the sense above will be the complement of a hypersurface inside my quadric. And the hypersurface that I choose is the locus cut out by this equation. So x12, x23, x34, x14 equals 0. These are those Plucker coordinates that are indexed by consecutive indices. So the first two columns, the second and third column, the third and fourth column, and I want to consider indices in a cyclic order. So the first and fourth column will also be considered as cyclic Plucker coordinates. So, this hypersurface is a bit special because it's anti-canonical, and it's an ample divisor, and if you remove it, you get a scheme that is affine. So that's this part so far is a global description of the scheme. But it's also possible to think about it in a more local way as a gluing of smaller pieces. And it can be done as follows. So let's consider this quiver. So this quiver has 5 nodes and 4 arrows. 4 of these nodes are circled in blue, and I label them with the Plucker coordinates that I described just above, the ones that vanish on the divisor compactifying B. And then I label the node in the middle with one of the 2 remaining Plucker coordinates, let's say 1, 3. Now, associated to this quiver, there is a torus, an algebraic torus, which is the spectrum of the Laurent polynomial ring obtained by inverting all coordinates that show up as labels in the quiver. And you can think of it either as a 5-dimensional torus, or if you remember this, that these coordinates are really homogeneous coordinates, we can scale by one of them and really, let's say 1, 4, and then I'm just consider this as a 4-dimensional torus. So there's a procedure you can perform on quivers, and that's called quiver mutation. And in this case, if you mutate at the only label that does not come from this divisor, the boundary of V, quiver mutation just flips, in this case, the direction of all the arrows. And there is a way to also mutate the labels. And the rule is that the product between the old label and the new label will be a sum of terms, a sum of 2 terms. The first is the product of the incoming labels, x12 and x34. And then the second term is the product of the outgoing label, x14, x23. So in other words, the rule that mutates the label is just, in this case, the relation that tells you that this is a quadric hypersurface. And you can think of it, if you solve for x24, as giving you a birational map phi12 between the torus associated to this quiver and the torus associated to the second quiver after mutation, after this mutation. So these 2 tori, together with the gluing birational map phi12, can be glued using the construction I was talking about earlier, and they give you a scheme U that happens to be not affine. In fact, if you try to take the affinization of this scheme, which means you look at the algebra of regular functions gamma U structure sheaf of U, and then take spec of that. For an affine scheme, you will get U back, but U is not affine. In this case, you get B, which is the original complement of the divisor. And to convince you that this is strictly larger, I wrote here a class of matrices that in fact belongs to the complement B minus U. So if you take a matrix that has some non-zero entries at the stars and zeros like this here, then 1, 2 will be a non-zero Pluker coordinate, 2, 3 will be a non-zero Pluker coordinate, 3, 4 will be a non-zero Pluker coordinate, 1, 4 as well. However, this matrices like this do not belong in any of these two charts. And the reason is that if you look, for example, at 1, 3, the Pluker coordinate 1, 3, that determinant will be 0. And same story for 2, 4. And so that means that these cannot be points in spec of Laurent polynomial rings because their 1, 3, and 2, 4 vanish, whereas they're supposed to be non-zero. Okay, so in general, I'm going to denote D and call deep locus precisely the locus you get when the affinization of a scheme is larger than the scheme itself. So there is another way to think about these points in the deep locus. So there is an action of a four-dimensional torus in my example, and it's just the action that takes T and uses T but to scale all the columns of the 2x4 matrix by the entries of T. So the first column gets scaled by T1, the second column by T2, and so on. Now, if you think about how the induced action on the Pluker coordinates looks like, it's just like this. The Pluker coordinates are homogeneous under this action. They get sent to a multiple of themselves, and that multiple is the product Ti/Tj if you act on Xij. So if you add, let's say, by the diagonal torus in C star 4, then this action will be trivial because remember, we're taking 2x4 matrices of full rank modulo row operations. And so the diagonal scaling does not change anything. But if you mod out by that diagonal subtorus, you get a torus that I'm denoting mathcal T, and that acts non-trivially on each chart, in fact. So the charts are invariant under this action because the condition for a point to be in one of these charts is precisely that its Pluker coordinates labeled by the labels of the quiver do not vanish. And since we're just scaling the Pluker coordinates by some non-zero terms, the non-vanishing or not of a given collection of Pluker coordinates is invariant under this action. Now, there is an observation due to Vivek Shende, and the observation is that in examples like these and more general examples called positron varieties, in fact, this action, and in fact, even more general examples that they'll describe later, this action on the charts is actually free. And so, consequently, if we denote S the locus of points that have some non-trivial stabilizer, then this locus needs to be necessarily contained inside the deep locus. And just to convince you that this gives you yet another way to think about these points, if I take one of the previous points that I was describing in the deep locus, you can easily verify that these points have some non-trivial stabilizer by looking at the action of this particular points of the torus on one of these matrices. So it turns out that these matrices have the same Pluker coordinates as the original matrix. And the reason is that when you scale by this factor one of the matrices, if I is equal to j modulo 2, then we're talking about determinants of this kind or this kind, and so they're zero in both cases. And if I is not j modulo 2, then we're talking about this kind of determinants, and they're equal to their analogs without the t factor, without the t scale. Now, the theorem I'd like to talk about today is a special case of a more general conjecture that I think that is also in our work paper, and I think is at least as interesting as the theorem. And the conjecture is the following. So we conjecture that if you have a scheme such that the ring of regular functions is a skew-symmetric and locally acyclic cluster algebra, then the stabilizer locus is actually equal to the deep locus. So let me try to give you some context to understand the meaning of this statement. So first of all, this statement is related. You can think of it as an answer to the question, when is a gluing of affine schemes affine? In the special case where the pieces are algebraic tori of a fixed dimension, and the gluing maps are of a particular form, which is essentially a Quiver mutation like the one I was describing earlier. But of course, it's a conjecture. That's not a theorem yet. So what does skew-symmetric cluster algebra mean? So a skew-symmetric cluster algebra is the data of a family of quivers labeled by some rational functions xt in the function field of V. So I'm denoting the quivers qt and xt. You can think of these quivers as being parameterized. So the index t, you can think of it as a node in an infinite tree that has an initial root denoted by t naught in my picture. And then each of the quivers in the family is related to the root by a sequence of mutations in the sense of quiver mutations. So for example, I will have a first generation of quivers that are obtained by choosing some way, a way to mutate from the initial quiver to a new one. And then from each of the children in the first generation, I will have for all possible mutations that you get by mutating all possible ways of their nodes, and so that will give me a second generation, and so on and so forth. And remember, besides mutating the quivers, we also mutate the labels, these rational functions. And so at each step, there is a torus associated to the quiver, which is the spectrum of the Laurent polynomial ring in the variables that are labeling the nodes. And overall, we can form a subalgebra of the function field of V, which is the algebra generated by the labels that show up in all mutations. So as you mutate, you'll see more and more labels showing up on your quivers. You put all of them together, and you take the subalgebra, some huge subalgebra generated by all these labels. So infinitely many typically. Okay, so that's for you the quick definition of skew-symmetric cluster algebra. It's called skew-symmetric because sometimes people define cluster algebras in terms of matrices instead of quivers. If you do that, there is a more general definition where the adjacency matrix of a quiver is skew-symmetric. But if you define things with matrices directly, it turns out you can define a more general notion of cluster algebras where you only allow where you allow skew-symmetrizable as opposed to skew-symmetric matrices. So in this generality, there is a notion of deep locus and stabilizer. The deep locus will simply be V, your scheme, minus the union of all the tori. And the stabilizer will be the stabilizer of a natural torus that acts on everything. And it's the torus of automorphisms of V such that they scale each set of label by some non-zero factor. Sorry, that scale each cluster variable by some non-zero factor. So if you look at a given set of labels, labeling some quiver, the action of the automorphism scales them by some non-zero factors. So so that's the generality in which we state this conjecture. Let me also say what locally acyclic means. So the example I was discussing earlier is a quiver that has no loops, no oriented loops. In general, we say that a cluster algebra is acyclic if at some point in the mutation process you see a quiver that has no oriented loops. Locally acyclic is a weakening of that. We only ask V to be covered by finitely many varieties that are clustered and such that each of them is acyclic. So each of them will have a family of quivers, and at some mutation step in this family of quivers, you want to witness that there are no cycles. So local acyclicity is a technical condition that, a priori does not seem to have a clear geometric meaning, but it turns out it rules out lots of potentially pathological examples. So some things that are true under this assumption are, for example, that V is indeed the affinization of the gluing of the charts. This does not be the case in general. And then other things that are true under these assumptions are that V is a finite type scheme. So that means that this algebra that a priori is infinitely generated is actually finitely generated. It turns out to be normal, and in fact a local complete intersection, and it's also pretty nice to work out a criterion for when it's a regular scheme. Okay, so and we have some counterexamples to the conjecture without this technical assumption. So the theorem we can prove is the following. So we can prove that the conjecture holds when there are finitely many seeds, or in the simplest case when there are infinitely many. And that case is the case of the Grassmannian 3n minus the analogous divisor analogous to the example I was telling earlier. So you take the divisor cut out by the Plucker coordinates, now indexed by 3 indices that are indexed by consecutive indices I, j, and k in cyclic order 1 through n. And so this turns out to be a scheme of cluster type that has infinitely many charts if n is large enough, and it's one of the simplest, and so we can prove the conjecture here as well. In this case, a byproduct of our theorem is that we can completely say when the deep locus is empty, or in other words, there's a gluing of tori in this case, and it happens if and only if 3 does not divide n. So let me say a little bit, let me explain a little more 1 and 2. So what does it mean that the set of seeds is finite? So remember that as part of the data of this cluster variety or cluster algebra, we have a quiver and some way to mutate this quiver. So here's another example that is slightly more complicated than the one I was discussing earlier. And so to each such quiver, you can associate a matrix like this, which is roughly the adjacency matrix of this quiver. So on rows, you put the indices of all nodes, and on columns, you put the indices of only the nodes that are mutable in the sense that they do not correspond to Fukaya coordinates for this compactifying divisor. So there will be a part of this matrix which really is the adjacency matrix of the mutable part. And so there's a way to cartonize this matrix by replacing the zeros with twos and by taking all the other entries with a minus sign. So if you do that here in this example, you will get a Cartan matrix, and it will be the Cartan matrix of a Dynkin diagram or a root system. And in this case, it will be A2 in my case. So Fomin and Zelevinsky, after introducing cluster algebras, they realized that this is something you can always do to a cluster algebra. You can always cartonize a certain part of the mutation matrix and get some corresponding root system, and they used and they were able to show that the root systems of finite type precisely correspond to cluster algebras such that when you mutate, the possible sets of labels that show up on the quivers are finite. There are finitely many sets. So in other words, the gluing process has finitely many torus pieces. So if you inspect, so the second point is what to. So this kind of spaces, the complements in the Grassmannian of the cyclic vanishing Fukaya coordinates are called top pository strata, and they are among the first and simplest examples of cluster schemes of cluster type. And the reason why we focus on this one in particular and why we think it's interesting is that if you look at the cases 2n, so Grassmannians of two planes in Cn, they turn out to be all of finite type, A1, A2, A3, A4, A5, A6, and so on. So they can all be constructed as affinizations of a gluing of finitely many tori. But if you go in Grassmannians 3n, the first few, 3.5, 3.6, 3.7, 3.8, are finite type A2, D4, E6, E8. That's a non-obvious statement, but trust me on this. But from 9 on, they turned out to be all infinite type. So they all are affinizations of gluings of infinitely many charts. So point 2 gives you evidence for the conjecture, the first evidence in the case that there are infinitely many charts. Okay, so let me explain some of the ideas that go into the proof of the theorem. So one first input is the fact that we don't think about these varieties. So I'll explain both 1 and 2. I guess focusing on the example of positrates. When I take k equal 2, that will be relevant for our proof of 1, which also extends away from type A in types A, D, E, because those are the schizommetric finite type ones. However, I'm only going to explain in type 2n, in type A. And if you take k equal 3, then I will be talking about the second part of the theorem. So the first input in the proof is to start thinking about these varieties not as complements of a divisor in the Grassmannian with the cluster structure given essentially by the Fukaya coordinates, but in a different way. So we think of these varieties as certain varieties as stabilizations by a torus of certain varieties associated to a braid word. So from now on, I will denote beta equals sigma 1 sigma r, sigma 1 sigma r, a word in the Artin generators of the break group. So these are, so I will call this some Artin generator of the break group. So something like this. Okay, so this will be, for example, I plus 1, I plus 1. So there are certain varieties associated to braids, positive braid words, and they're defined like this. So you look at, let's say you have a word of length r, then you look at tuples z1 through zr in C to the r that satisfy the following. The Demazure product of beta inverse times beta z1 zr is upper triangular, where the Demazure product of a braid just means think that braid as, read that braid from left to right, interpret each Artin generator as a permutation in the symmetric group, and if the next Artin generator decreases the length of the current product, then throw it away. If it increases the length, then take their product, and so on and so forth. So that's called the Demazure product. Gives you some permutation Sk, and you can think of Sk as a subgroup of Gk by identifying permutations with permutation matrices or permutations of the identity matrix. Beta z1 through zr is instead, you can think of it as a deformation, multivariable deformation of a permutation matrix. So an Artin generator, as we said, is ultimately some transposition in terms of permutations, and you can think of that as a, imagine a zero here, as a matrix by permuting the corresponding columns of the identity matrix. Now you can make that into a one parameter deformation by turning that zero into a z variable. And if you do that for each Artin generator that shows up in the braid, you get a multi-variable deformation of the braid. And you can think of it as an invertible matrix with entries in the polynomial ring C z1 through zr. So overall, when you take this product, you get some matrix, and you ask this to be upper triangular. That's a condition that cuts out a bunch of algebraic equations, and those are the equations for this affine variety x beta. It turns out this is a smooth variety of dimension r minus the length as a permutation of the Demazure product of beta. And so what I was saying earlier is that you can think of this positroid, at least the top positroid strata, as one of these braid varieties times a torus. And the braid in question is, if you want some explicit formula, can be written explicitly. It's some braid called the half twist, written here, times sigma k minus 1 through sigma 1 raised to n minus k. I'll draw some pictures later. Now, the second ingredient in the proof is to realize that the torus action that enters the definition of stabilized locus, remember the conjecture is S equal D, stabilized locus equals deep locus. So the second step is to realize that this kind of symmetries, this torus action, are actually equivalent to some symmetries that stem from the braid presentation. So the torus action on that we were talking about earlier is isomorphic in the sense that there is an equivariant isomorphism here to the one given by a different torus action times a torus that acts on itself on the right. And this torus action is defined in terms of the braid, and it's defined like this. So you look at the diagonal torus inside GLK, and you mod out by the multiples of the identity. The diagonal matrices where the diagonal entries are all equal. And the braid itself gives you a natural way to act on C to the R by rescaling the coordinates by some weights C1 through CR. And so I'll describe in some examples how this action works. So imagine your braid to be, for example, sigma 1, sigma 1. So that's 2 times the first Artin generator. So you see the picture here. Then you label the strands T1 and T2, and then you label the crossings Z1 and Z2. And then the action of T on Z1, Z2 will be rescaling by some weights, and the weight of Z1 will be obtained by following the strings that enter Z1 from the left and taking the ratio between the label of the lower string and the label of the upper string. So T2 over T1 in this case. For Z2, you do the same. You follow the strings that enter Z2 from the left. You take the ratio of T1 over T2 because T1 is the label of the lowest string and T2 is the label of the upper string. Okay, and here's a more complicated example on 3 strings. This is the braid sigma 1, sigma 2, sigma 1, sigma 2, sigma 1. Again, we have 3 strands, so three weights, T1, T2, T3, and then you have braid coordinates, one for each of the Artin generators in my braid word, and the action, for example, on Z3 will be obtained by following the strands that enter Z3 from the left, and it's T3 over T2. So it turns out that this action, which is quite combinatorial to define, is roughly equivalent to T in the sense that this torus action times the trivial action of the torus on the right factor makes this variety equivalently isomorphic to the previous one. And this action is very handy. For example, it's very easy in this model to say when the stabilizer locus is empty. Turns out to be empty if and only if the closure of this part of the braid has pairwise unlinked components as a link, and that ends up being equivalent to the GCD of K and N being 1. So this input allows us to figure out very explicitly what the stabilizer is. Let me mention the last ingredient that enters the proof. So the last ingredient is it's the following. So there is a notion, there's a kind of notion of cobordism between positive braid words called weave that has been introduced by Casals and Zaslow. And so I'm illustrating with, instead of giving you a definition, it will be too long. I'm illustrating with a picture an example of a weave. So let's say we want to describe a weave, or think of it as a cobordism between 2 words, beta 2 written here and beta 1 written here. So how does that work? We write the words on top and bottom as strings of Artin generators, and then we color Artin generators of the same type. So sigma 1, sigma 1, sigma 1, sigma 1 are red here and red at the bottom. Sigma 2 gets a blue color, sigma 3 gets a green color. And now the game to construct a weave or a cobordism, the rule will be that for each color, you pick a trivalent graph that joins the upper instances of the Artin generator to the lower instances. So for example, if I only look at the Artin generator sigma 1, the trivalent graph that I'm picking here is this one. Okay, so trivalent means that each of the nodes has degree 3, except the ends. And so as you see, it connects the upper instances of sigma 1 and the 1 of sigma 2. And you do the same for sigma 2 and sigma 3. So this will be a part of the graph, that trivalent graph that joins the upper instances of sigma 2 to the lower ones. Okay, I'm not going to draw all of it. And there's a second rule, and the rule is that once you have a trivalent graph for each color that joins top and bottom, you impose that if two graphs intersect, then if they correspond, like here, to Artin generators that are far apart, meaning they differ by at least 2 in the index, remember, those in the braid relations are the ones you can commute, then there is no constraint. They can intersect as they like. But if you have two trivalent graphs that correspond to adjacent Artin generators, remember, those are the ones responsible for the braid relations in the braid group, then you ask that they only intersect at trivalent points. And when they do, they form an hexavalent pattern like this, where the colors alternate. So blue, red, blue, red, blue, red. So that's a weave in a nutshell. And the key fact that I'm not going to explain here in any detail is that whenever you have a weave, just like a braid gave you a variety, whenever you have a weave, there is a way to write down a correspondence between the varieties at the bottom and at the top. I'm denoting the correspondence of varieties like this. And it turns out that if the braid at the bottom is the Demazure product of the braid at the top, and the weave has no cups or caps, then this error of the correspondence construction is actually an open embedding of a torus of dimension 3 times the number of trivalent vertices. And so weaves give you a diagrammatic way to describe cluster charts or torus charts in your space. And so in particular, they allow you to explicitly construct, you remember, by Chandra's observation, we know that if a point has some stabilizer, then it must be in the deep locus. And our conjecture is that these are equal. So we want to prove that D is inside S. And what we prove is that the complement of S is inside the complement of D. And the way we do it is we take a point that is not in the stabilizer, so a point where the action is free. We understand these points very well because of the previous slide. We understand the stabilizer very well. And then the game is for each such point to try to construct an explicit chart that witnesses the fact that that point is not in the deep locus. An explicit chart that covers that point in the union of all the charts. And we do construct these charts by constructing the corresponding weave. Okay, so that's the logic of the proof. And so if you open up the paper, you'll see, it ends up being relevant only to work with essentially 2 and 3 strands, and we're able to solve these kind of problems with this diagrammatics. When the number of strands increases, then the story is a bit different, but okay, so I think it's a good time to stop for a break. Yeah.
Yeah, excellent. Thanks very much. Yes, we'll have a short break, let's say until 5:19.